All right, everyone. How are we doing today? Doing all right. Okay. So, a couple sections left of new stuff. Today, we're going to be talking about one of our two final theorems. It is called Stokes' theorem, and what this does is it relates a boundary integral to a surface integral. So let's start with our previous result that related two types of integrals. Green's theorem. Okay. Basically, for Green's theorem, we have a picture of some domain, and I think about the integral as being in two parts. I have some positively oriented boundary curve, and then I have this included domain here. All right. And what we showed more or less is that if I have a boundary curve C and a domain D, that under the right conditions, the closed path integral around the boundary was equal to the we'll write it using the vector notation. Okay, so we have this kind of expression. All right. This, of course, works because we are imagining that f is given by those component functions. Okay. Now, Stokes' theorem is related to this, and basically can be thought of as a slight generalization of this idea. For Stokes' theorem, this is a vector field, and we are integrating either the vector field in this region or along the path. Sorry, lots of descriptors here. Okay, so let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth curve C that's positively oriented. Okay? F is going to be a vector field. The components have continuous partial derivatives. The statement of the book of the theorem in your book doesn't specify first, but when it says continuous partial derivatives, that means that it has at least one continuous partial derivative. All right. So, a lot of words because there's a lot of things that we have to specify about the surface. All right. We have a surface that's embedded in three-dimensional space. Okay. So if I were to draw the picture of the surface, it would be something like this. Okay. It's sitting in space. All right. And I can think about it as being I think about it sitting in 3D, which is how we've drawn the picture here, right? In some open region that contains the surface, okay, so I can eclipse it in an ellipsoidal shape or whatever, okay, or just kind of a fuzzy shape that barely surrounds the surface, however you want to do it, all right? But inside of that region, the function needs to have nice calculus properties, okay? And then I imagine that there is some vector field in the environment given to me by F that this thing is sitting in. Make sense? Okay. So the vector field comes from F. I'm sorry. Yeah. No. It is just a surface. It has no volume. All right. Okay. And what is going on here is Stokes' theorem is relating the idea of integrating over the boundary to integrating with respect to the surface in this vector field. Specifically, the curl of F over the surface. Okay? This is the curl of that vector field. All right, so what we're seeing is, in some sense, how much the vector field tends to twist as it's passing through that surface. Okay? And the total amount of twisting that is done inside the region can be detected at the boundary. Okay? That's a pretty powerful thing, right? I can determine the interior behavior by just looking at what's going on the edge. Okay? Also, I want to point your attention back to Green's theorem up here. This is the 2D version of Stokes' theorem. If I have the same setup and instead my surface is flat, it does not change in the z direction, then the formulas are the same. Because any derivatives that had to do with z would be equal to 0, right? And my surface integral would flatten out, and I would get exactly that term when I computed the curl for the only surviving component. Okay? So these two things are very closely related to one another. All right. Yes. Yeah. But you can have the comparison between Green's theorem and Stokes' theorem is that if I were to flatten out, basically, if I had a surface that was flat, it had no z component to it, and it sat in the xy plane, when I set up my integral equations, Green's theorem and Stokes' theorem would give me the same thing to compute. All right. Let's evaluate this integral, the path integral through the vector field f. We're given f is going to be equal to negative y squared x z squared. Okay? All right. So we have this expression here. All right. So we want to evaluate this integral. We want to look at the vector field negative y squared x z squared. And we want to do our integral where C is going to be the intersection of an inclined plane and a cylinder. We make a sketch. We have the cylinder of radius 1 that looks like this. Okay, quickly sketched. XYZ here. Okay, and then we also have some plane that comes through and cuts like this. And we're going to get a circle, or sorry, an ellipse that looks something like this that sits on the plane. So it's kind of like the example that we had last time where we have basically like a paper towel roll that someone cut through at an angle. Okay, and we want that top circle that's on the where the cut occurred. All right. So let's set up to use our theorem. Okay. We could integrate along this path, but we'd have to figure out a parameterization for the path, and it's probably going to be easier just to do a surface integral instead. So that is going to be our plan. We're going to start setting up that integral by looking at what the curl of f is. Okay, so we set up to do this computation here. Work things out. We do this computation. Those are both 0. We take those partial derivatives. This partial that is 0. That partial this is 0. Okay. Then we do the middle one. 0, 0. And then we look at the last one. We finally get something that we can do something with. We get 1 minus 2y. Or sorry, 1 plus 2y, excuse me. Forgot the minus sign on the AD minus BC. All right, so we have this. All right. Now, we are wanting to set up the use of our theorem here. Okay. Sorry, I'm double checking something. All right. Just for clarification purposes, this dot ds notation, and do note that I have been underlining the s here. The way that this is interpreted is it looks like this. Okay, so the dot ds that's bold faced, we think of as dot the normal vector to that surface, and then with ds that is not bold-faced. Okay. So the idea of a projection is built into the way that we use the notation here. So in the particular example that we're looking at, what happens is we are going to rearrange this equation, solving it for z. Okay, so we get 2 minus y here. And this element ends up looking like this. Due to the nature of the projection. So when we why can't I find this? Oh, I'm in the wrong section. Goodness. That's why I can't find it. I'm also out of room. Okay. All right. So what this is a shortcut for this formula where the f here has been replaced with the curl. Okay. Now, on this surface here, I have this equation for z, all right? And this is the thing that that formula calls g. All right. So there's a few moving parts here. So if I differentiate this with respect to x, I get nothing. If I differentiate it with respect to y, then we're going to get -1. And for r, okay, let me say all the words here. Sorry. We have the curl of f, and that's replacing f in this expression. Okay? The curl of f is 0, 0, 1 minus 2y. Or 1 plus 2y, sorry. I made that mistake twice. We have this, okay? This is our f in the way that this formula is written out. And we want to compute this product here. P is 0, Q is 0. So we need to know what this G is in order to be able to use it in the formula if we needed to. But both of those are taken out by the P's and Q's already being 0. And then we have R here as the 1 plus 2y. So that is why we get this as the integral to compute. Okay. Okay, this is a special case formula from 16.7. It's formula 10. All right. It's when you have when your surface is a graph, you can use this formula. So if the surface can be parameterized in terms of x and y, then we have access to this formula. All right, so we're integrating here now. The domain that we're integrating in is the unit disk. So it makes sense for us to switch to polar. Sorry, I forgot. It should be 2r sine theta. All right. Okay, so fix that. Should be an r there for the switch to polar. And now we have something that we can work on integrating here. We'll integrate with respect to r first. We can integrate term by term, so this isn't so bad. We distribute the r from r d theta, so that gives us r plus 2r squared sine theta. We integrate r to get r squared over 2, and then we integrate r squared to get 2r cubed over 3, and then times sine theta. We're going to evaluate this from 0 to 1. It leaves us with 1/2 plus 2/3 sine theta d theta. We can integrate this. We're going to end up with theta over 2 minus 2/3 cosine theta. And then we take a look at what's going on here. So we're going to get 2 pi over 2 minus 2/3 cosine 2 theta plus 0 and minus 2/3 cosine of 0. So we get pi, because I wrote the wrong thing. All right, sorry, that should be my sign. Today's not my day. Sorry about this. All right. So we have 2/3, and what's the cosine of 2 pi? And then minus minus, which is a plus. And what's the cosine of 0? So we just get pi. Okay. If we were really thinking about it, I don't know if that's a helpful thing to say or not. Yeah. I'm gonna leave that one alone. There's a geometry thing that we could have noticed about the sine integral, but it's not the way that we're used to thinking about it. So I'm gonna leave it alone. Okay. So sorry about getting us bogged down in the calculations there a little bit. I was trying to cover some of the things that we didn't talk about last lecture, and I got jumbled up trying to organize the ideas. In summary, however, what we're doing is a higher dimensional version of Green's theorem. Okay, we have a new version of it. All right, and the idea is that we have a surface that we are placing in a vector field. Okay, and in that surface, we can detect the curl along the surface of that vector field by just examining what happens at the boundary if we have a nice enough surface and a nice enough boundary. Okay. So the yeah, the I don't want to use the wrong vocabulary here. So when we are looking at a surface like this, so just to keep things easy, imagine that we have the idea here is the same as if we have a sort of flat surface or my words have left me. Okay, we have a circle here. Imagine that I have a vector field that is flowing towards me. Okay, now I'm using the convention here that uh, dot is the arrow coming at you and X is the arrow going away from you. Okay, so dot means coming out of the page. All right. Now, what Stokes' theorem is measuring is if instead of all of these dots coming directly at me, some of them were coming at me and I maybe had a few that were going away or whatever. I can only really draw two directions in this picture. But in order for this to happen, there has to be some kind of circulation that's occurring as that vector field passes through the place enclosed by this boundary. Okay? So when we're talking about the curl, what we're imagining is if you have a flow, and we can imagine the flow moving sideways or something, all right? There's going to be, at some points, a twist. Okay, so if we have a bunch of streamlines of water flowing in a direction, all right, if the water is changing direction, there are multiple ways that the water can move. All right, it can translate this way, up or down. It can translate left or right, but it can also twist. Right? We can imagine the streamlines twisting. And Stokes' theorem essentially is measuring the total amount of twisting that happens in the streamlines that pass through the surface in that vector field. Okay? Now, it turns out to be an extremely important consequence of Stokes' theorem that, say I have a boundary that sits flat in the plane, so this picture is going to be as easy as I can to draw it, right? So if the surface that I care about is this, and I use Stokes' theorem to measure some vector field that is passing through this, okay, the amount of twisting of these streamlines that I measure is going to be some amount. Now, if instead I imagine that I have a surface that bulges out a little bit, it's still positively oriented, so the normal vectors of this surface point in the same direction as the one that I had before, okay, I would get the same answer. All right? If I have a much larger surface that has the same boundary on the bottom, that total twist that I measure for the vector field as it passes through is going to be the same. All right? So what I can do is, by taking this measurement on the boundary, I can identify, that is, treat of as members of the same class that have the same behavior, all of the surfaces that share a boundary, as long as they're all positively oriented and don't break any of the rules. Positively oriented in this sense means that if I were to use the right hand rule, so this will be extending your right arm out to the right and pointing your index finger to your right hand side, and then your middle finger points in towards the domain. Okay, so that's inward. I'll draw it kind of oblique like that so it's easier to see. Then you have a normal vector that points upward. Yeah, so your thumb is this is how you tell that something's in a positive orientation. Okay, if it's flat, like this picture here, what you get is clockwise, where that big dot is your thumb pointing back at your face. That's the positive orientation. Okay, so your index finger points along the boundary, your middle finger points towards the interior of the domain, and then your thumb on your right hand will tell you what direction the normal vector is in. It'd still be positive down into the surface as long as your boundary direction was down counterclockwise, correct? No. So part of positive orientation is that we imagine that our index finger is tracing counterclockwise. Yeah, so counterclockwise for one, counterclockwise along the boundary, and then the vector that you're crossing with is one that points into the domain. You use your right hand. Use your right hand, go counterclockwise. All right. But it's actually really important that all of these surfaces have the same behavior under Stokes' theorem. Okay? This tells us something very powerful about flows, too. Okay? If I try to do this kind of measurement in a conservative vector field, what's going to happen? How do we tell that a vector field is conservative? The curl what? Curl is 0. What's the formula for Stokes' theorem? There's a curl in there. Oh. A path integral gives us 0 if we do a closed path inside of a vector field, right? Okay. Also, the curl of that vector field will be 0. So we get all of this, all right? And we also know, of course, that the curl of a gradient is 0, right? That's how we know that that's true. All right. Okie dokie. So I talked about the idea of the streamlines twisting, right? Just to use a proper vocabulary term for that, this is circulation, okay? And one of the ways that we can detect this is if we're doing the integral kind of in this sense where we're moving around a boundary, all right? There's going to be a tendency for the vector field to try to twist my vector that I'm integrating with respect to. Because when we when we do a path integral in a vector field, what I'm imagining doing is I'm imagining taking this vector, and I can't twist it when I'm dragging it around, but I have this vector and I'm moving it around and doing my measurement, right? Now that arrow obviously should have stayed in the tangent direction and twisted along with the picture, but I can't do that. And what's happening is my integral measures basically how much the vector field is pushing on me as I travel along that path. Okay? That pushing in this instance takes the effect of trying to twist that vector. Okay? And as I move the vector around, I'm measuring that total amount of twisting. Okay? And that twisting is what we call the circulation. Okay? So the other way to think about it is if the circulation is high, it's the tendency of the fluid itself to kind of have a vortex behavior around that path. Okay? If the curl is 0, then there's no swirling of the fluid. You get 0. The the curl being 0 is just a case of there's not any interesting behavior. Not any interesting behavior in this regard. Let me be more clear about that. Okay. The more carefully stated, Stokes' theorem gives us the information that says that if the curl of a vector field is 0 everywhere, then we have a conservative vector field. Okay. Stokes points that direction, or points that argument kind of in the opposite direction. Basically, what you can do is if the curl is 0 everywhere, then that means that want to be clear about how we say this. We know that a vector field is conservative if the integral is 0 along every closed path, right? If the curl is 0, then this integral is going to be 0, which means that this integral is 0. Okay, so that's how Stokes' theorem implies that conservative vector fields, if the curl is 0 everywhere, then a vector field is conservative. All right. What I want to do is talk about, or I want to briefly introduce the idea from section 16.9 so that we have these two things sitting side by side so that we can next time put everything in context. Okay, this is called the divergence theorem. People don't call it that. So I wouldn't, people just refer to it as Stokes' theorem. The more common thing to do actually is to call it Green's theorem. It's just Stokes is a generalization of Green's theorem. All right. There are a lot of hypotheses. I'm not going to copy them down right now. We'll mess with that later. Okay, so this is called the divergence theorem. All right. E is a simple solid region, and S is a surface that has all the properties that we think of a nice surface having, except S is a closed surface because it is the boundary of the solid E. Okay, so S might be the surface that like is the boundary of a cube or something. Okay, or it is an ellipsoid on the surface of some 3D region. Okay, so these are the kinds of surfaces we're talking about for this theorem. Basically, what the divergence theorem says is that the flux through the boundary is equal to the divergence integrated over the entire volume. Okay? Now, this theorem has a couple of other names. It is sometimes referred to as Gauss's theorem or the Gauss-Ostrogradski theorem. It's hard to say. There was a while in history where the Russian mathematicians were not talking to the rest of the European mathematicians. So there's my PhD advisor is Russian, so there's a lot of theorems that have two names. Anyway, but this is a pretty famous case of where there was no way that either of these guys, Gauss or Ostrogradski, knew about each other working on this, so they developed it independently. So it happened in the early 1800s, which is when this happened. It also happened again during the Cold War when the Russian mathematicians were not talking to the rest of the European and Western mathematicians for different reasons. Uh, anyway, this is Gauss's theorem. Okay, I imagine that some percentage of you have taken physics too. Okay, now you probably don't do the volume integral version of working with Gauss's theorem here, but you may have talked about problems where you maybe have some charge distribution that's in a region, and then you say, you know what, this is all inside of a sphere, and then you use the sphere to very easily figure out what the contained charge is. This is the theorem that does that. All right. So we'll look into that next time, and then we'll do a little bit of talking about how kind of all of the pieces for this fit together in terms of these three major theorems. We have Green's theorem, which is generalized into Stokes' theorem, and then also the divergence theorem, which is often applied in physics classes as Gauss's law. All right, so take care, everybody, and I will talk to you next time.